I'm here to speak about distributed monitoring and a little bit about distributed tracing and how to understand the complexity behind distribution. So I'm Gianluca Arbezzano. I work for InfluxData as a SRE, as a site reliability engineer, and you can find me on Twitter, and I have a blog where sometimes I write stuff. So. As a site reliability engineer at InfluxData, my daily job is to support our SaaS and IaaS offers. So we have a product that people can buy, and they have InfluxDB and all the tech stack as a service. We use AWS as a cloud provider. So my daily job is to deal with AWS, clusters, and stuff that doesn't work. So that's mainly what I do every day. Other than that, I like to make dirty hacks to look great. So this is one of the stuff I do. I like to grow vegetables. So I have a garden. And I like to travel for fun and work. I also cook. This is my attempt to make gnocchi. So it was great. I told you that I have a garden. This is definitely not my garden, but that was great. And yeah, I was in Cuba a few months ago, looking at the sea and thinking about monitoring, because that's what I do every time I have some free time. So I was thinking deeply about distributed system, how to improve my monitoring, and how to get something useful from all the data that we generate. So it was a really great experience for me, and I thought that I was in paradise. But when I started to think about how the stuff was going, I thought that there is definitely something wrong, because a lot of stuff changing over this time. We have containers, we have Kubernetes, we have, stronger hardware, we have a deeper distributed system. We don't have a monolithic anymore, but we are always looking at a line graph in some dashboard at the hand, and we always get paged when something goes wrong. So why everything changed, but monitoring is still kindly like the same? So I'm gonna carry you with my journey through monitoring and what I learned after 1.5 years at InfluxData, just doing monitoring for people that are looking to monitor stuff. So we have a solution to monitor things, but we are also learning a lot using ourselves, and this is what I learned. So if you don't know anything about InfluxData, we have a set of open source tools that you can use to build a monitoring stack. So the most famous one is called InfluxDB. It's a time series database that you can use to push your metrics and to query it using a SQL-like language. Other than that, we thought that it wasn't enough. So we was able to cover stuff like DevOps monitoring, so you need to find a way to get the metrics out from your system and push them to InfluxDB. A lot of people was using our database as an IoT solution because all the sensors, temperature, pressure, and this kind of stuff are time series because times matters a lot in this kind of metrics, but it wasn't enough. So we started to open source an agent called Telegraph that now has more than 200 plugins that you can use to gather metrics from a lot of services, from CPU, memory, to MySQL, or whatever you want. And it has two concepts of input and output. So you can even output stuff not in InfluxDB, but in other stuff like CloudWatch or Prometheus or whatever. Other than that, we released Chronograph. This is a UI. You can use Grafana also. It's compatible by default. Chronograph has more capabilities related to management of all the stack. So you have user management and this kind of stuff. The last one is Capacitor. It's our post-processing data and stream processing. So you can write what we call tick script to take action on the metrics that you are listening. The base action, usually, as I said before, is a page. So you listen to all the metrics and you teach Capacitor where to alert on something. So it can be a PagerDuty page or a Slack message or whatever you want. But you can do something more, stuff really a lot more complicated. Like you can real-time stream data from InfluxDB, compact them, aggregate them, and move them to another source, like in another database or in InfluxDB again, to create loops and downsampling data, and so on. So give it a try. But I'm here to speak about distributed system. So if you are thinking that distributed system is only for microservices or hipster people, you're wrong. Because we are using distributed systems since ages, because a queue system is distributed. Obviously, microservices are distributed in a different way, because usually they go over the network a lot, so network fails, so it's a mess. But a queue system, it's still a distributed system. A multi-thread application is a distributed system. It's not distributed over the network. It's distributed over cores and threads, but it's still distribution. More something is distributed across servers, across worlds and regions, across cloud providers, and more complex it is. It's more complex to develop. It's more complex to understand when something breaks. It's just more complex. So containers, Docker, Kubernetes, cloud computing itself. Cloud computing gives us a lot more capabilities in terms of distribution, because now we don't need to buy hardware anymore. We don't need racks. We just need few API calls, and we can go from Ireland to US in a second. So obviously there is latency, but it's more affordable. So all these tools increase the amount of complexity we are giving to our application. We get a lot back because we get a lot of flexibility, we get high availability, but it has a cost. So if you are one of the people that migrated to microservices container without a reason, blame yourself, because now you need to manage a complex system. In a distributed system, a request doesn't go through a funnel and X from your application as it went in, just reach it with all the features you've wrote. It goes spread around a distributed system. So maybe you start with a request from a customer that called your API or your front end, but you call a lot more services and a lot of more applications. You go in a queue, and everything become more complicated. And this is complexity, and we need a way to measure and to understand complexity. So the logs are not easy to follow anymore. There are a lot of them, but we are used to manage a lot of logs because we always had a lot of spam going on from our application. But the problem is that it's not a single stream. So as I told you before, when you have a monolithic, you have an application that gets in and gets out from the application. So you follow the logs, and you can kind of understand what's going on. But in a distributed fashion and microservices kind of architecture, you need to follow a request that goes over the network and come back and go on and come back. And sometimes it also goes to third-party services, because nowadays we use a lot more of third-party services and API compared with what we was doing before. So it's not a single stream anymore that we can kind of understand the tailing logs. So event and metrics and logs need to be correlated in some way. And correlation is really, really hard. I think that now it's really clear how we can get metrics out from a system. So we know Prometheus, we know that it exports slash metrics that we can read, and we know how to read CPU and memory from our system. We kind of know where to store them, if they are not too many. But they are hard to understand. At the end of the story, what I learned is that you are always asking for a new question, and you need to correlate and to aggregate data together to get answer to all these questions. So that's why I think that dashboards are great, but they are not the end solution. Dashboards are great to visualize a problem, but when you visualize it, usually the issue already happened. So that's why we have a lot of dashboards that just show you all their outages. And we look at them because we are scared about having this problem again. But usually, and I hope so for you and for your team, that the problems are always kind of different. So the goal for us is not to have the data, but is to have the ability to make the right queries and get the right answer from a database from where we store all the metrics. And if you follow the keynote, it's great because we can have metrics from everywhere. Like, it's just not our application that speaks. It's not just our infrastructure that tell us how it's going, but it's also our Git, our SVC, our Jenkins tell us a lot. So if you start to monitor Jenkins jobs, you get a lot of information out of it. So we need to have a place where we can store all the data, and for me, it's InfluxDB. And we need a way to query them, and we need to be smart enough to ask for the right queries. So nowadays, we have three kind of different representation of points in time. One is metrics that are events. Events can be regular or irregular. Regular events are like CPU and memory, so stuff that you take every 10 seconds. So these metrics are regular time series. But there are also irregular time series, like how many logs your application, how many login your application handle. This is not regular because we don't ask to our customers to log in every 10 seconds because it would be weird. So these time series that are not in order, they are irregular because they can come from wherever and whenever they want. So another representation of these metrics are traces. So based on the aggregation of this information, we can get a trace. I'm going to explain you what a trace is and how it looks like later. Another one that we know really well is log. Log is a point in time that, other than being just an event, it has a lot more information and a lot more context about what's going on in that specific point in time. Sometimes it's just a message that we typed, sometimes it's a panic or it's a stack trace. So a log is very important, but it is just a different representation of an irregular time series. So when I look at them, I see a matrix like a big slap in the face. Like, you get a wrong matrix and it's like a slap. You wake up in the night and you don't know what's going on. You just get this slap, and now it's time to figure out what's going on. So now that you are up, how you look at it, you start to make some queries, but now what I'm doing these days is just looking at logs. So I wake up and I take some logs, or I go in Elasticsearch or Papertrail, whatever, in my centralized log, and I look at how fast they are. If they are a lot faster than usual, maybe there is something wrong. If they are very, very slow, there is something wrong in some other place. So it's confusing me sometimes looking at logs. There is a better way to look at the picture, is traces. So traces, it's a different representation. Traces is just a different representation of points in times, and it helps us to understand how a specific request flows in our applications. So we are able to say, okay, from here to here it went to the front end, from here to here in the back end, from here to in MySQL, and this kind of stuff. So it's a different representation of the metrics. And as I said, the secret is all about how we combine all these data together. So traces is a way to correlate logs, and it's easy. It's just use a couple of IDs. So you have a trace ID. Every request has a trace ID, and you use this trace ID over all your system. So your logs has a trace ID, and you can look up for the logs that come from that specific request. So if you work with AWS API, for example, but there are a lot of other providers that use that, when you do a request, you get a request ID back. And usually that request ID back is the key that they use to look up the trace for that specific request. So they are able to see what's going on for every specific request. And this is very useful. If you are lucky enough to have an API that developers are using, or if you are good enough to show this number to your customer, you can ask them to give you that number, and you can go deeper and fix or debug that specific request that didn't work for them. So this is how a trace looks like. You know, this is a specific request. You have time and you have a set of blocks. These blocks are called span, and this span represents a specific application. So as you can see, my request goes to Nginx, that is my ingress, and they go to the API, and the API at some point call the out service to understand if the user is the right user. and it goes there twice because it needs to check the token and the role. At some point, it goes to MySQL, but before it asks for the authentication and this kind of stuff. So this representation in a distributed session world is really great. As I told you, this is good for microservices, but it is also great for queuing system. So let's swap this example, and you have a queue, and you have workers. If you put the trace ID in the payload of the message, you can trace how the message goes in your workers, how much time it took to process that kind of message, and so on. So it's great. You just need to try it. You will feel in love. So the problem, like when we start doing tracing, is that we write application in many different languages. So Go, PHP, Java, and Java for Android, Java for the backend, whatever. And we write it across different teams. So there are different people that are tracing different applications. But at the end of the story, you need to build a single trace that goes over all of these teams, all of these hands, and all of these people. So no matter the team, no matter the language. This is where a standard plays the role. So OpenTracing it's a standard sponsored by the CNCF, the Cloud Native Computing Foundation, that it is a branch of the Linux Foundation that is helping open source projects related to cloud. So Kubernetes is probably the famous one, but also Prometheus is incubated in the CNCF, and OpenTracing it's a standard that they are promoting to build a single trace out from different languages and different applications. So an infrastructure or the architecture behind OpenTracing looks like that. You have a set of libraries in different languages that you can embed in your application. These libraries are abstracting the backend of the trace, so the place where you store traces. This backend is called tracer. There are a lot of different tracers. Some of them are open source, like Zipkin or Jaeger. Zipkin is a Twitter project in Java, and Jaeger, for example, is a Go one released by Uber. But there are also closed as a service solution like Lightstep or AppDash or New Relic supports OpenTracing too, and so on. So the idea is that you instrument your application using the OpenTracing stuff, and no one cares about the end of where your trace goes, but it will just work. So it also removes a vendor lock-in that is kind of important. So it's more than 2 years old, but it has already a lot of support. So companies like Red Hat, Lyft, Pinterest, Apple are using the OpenTracing standard. And there is also a huge ecosystem of application and languages that are using it. So Spring Boot has an OpenTracing integration that works. Amazon has a service that is called X-Ray, where you can put traces. If you use gRPC supports OpenTracing, so you can just attach a middleware that it's going to create trace and spans from your gRPC application. Ruby has a library, PHP has a library, Objective-C, Android, so whatever. The problem is that trace is a high cardinality kind of data. Because if you think about that, the lookup point for a trace is the trace ID. But the trace ID is different from every request. So if you have a lot of requests, you have a big index to manage. And this is what high cardinality means. So they are really expensive to store, and that's why you need the right place to save them. Good for us, tracing as they are at the beginning doesn't have a really long life cycle. So usually if something gets wrong, you know that from the metrics in a day or in an hour or in 10 seconds, it depends. But usually after a week, they can go away. So it really depends, but you need, at first, a really detailed trace, but you can downsampling that, or you can remove that after a reasonable amount of time. So, for example, we remove traces after 7 days. We don't remove all of them. We sample them in something that we care, but we remove what we don't care. So I will show you later how our trace looks like. There are a lot of information. But sometimes what we just need after 1 year, for example, is, I don't know, the amount of time we spent code AWS. Like how much time our service spent calling the AWS the AWS API. So to answer these questions, you don't really need all the detail about the trace. You just need start and stop. Or you just need to aggregate the sum of all the span. So in Go, because I work mainly in Go, it looks like this. In the main of your application, you start the OpenTracing SDK, and you inject a compatible tracer inside it. So it can be the Zipkin one, the Jaeger one, it can be yours or whatever. So from this point in time, you don't care about the tracer anymore. You speak with the OpenTracing API. So if you need to change the tracer at some point because you are paying too much or you are paying too less and you need to pay more, you can change it without changing your code in your application, all the code in your application. So let's say that you have a function and you can start a span. So the trace is a collection of spans. So every block is called a span. And you start a span and you end the span when you wish. Usually you defer it when the function you are calling is over, you close the span. But you can also close it wherever you prefer. Now that you have a span, you can attach a lot of information like logs, or you can, there are a bunch of key values stored that you can use. For example, if you're tracing a MySQL request, you can store the user that made it or the query itself. There is also another piece that is called span context, and the difference, because it's another key value stored in the span itself. The difference is that the span context is propagated to the next via HTTP or via TCP or whatever is your protocol to the next steps. So you can have if you inject something in the span context, it goes over all the trace. If you use the key value store, the log, they are just for that trace. Another stuff that you can do is you can create child span for another span. So you can build the hierarchy of your spans and your requests. This is OpenTracing. I'm not going to go too deeper on this because there are too many languages and I don't know how many of you are used to it. So just have a look at the site and you will figure it out. Another good stuff that we do at Influx to monitor our system is that if a service doesn't expose the Prometheus format, it doesn't exist. So if it crashes, it's your fault. So every service inside has a slash matrix, and this gives us a huge amount of automation that we can build, because we can have Prometheus to scrape them, or we can have Telegraph, our collector, to scrape all the services and all the entry point that has a slash matrix. So every time that somebody deploy a new service, they don't need to do anything. Kubernetes or Telegraph just know that it's there and it's going to get the data. There is a huge fight between pull and push method for metrics. So if you know Prometheus, you probably use, and if you use Prometheus, you probably use the pull. You are used to the pull method. So the pull method is the fact that your application exposes the metrics, and there is something that is gonna pull them periodically. Now, this is great. This is really cheap because the aggregation is made before reaching the database, so you store less data. If you use Prometheus, you know that you have counters, you have histograms, you have gauge. So the aggregation is made in the application side and not in the storage side. But sometimes you need a push. So think about that push is the traditional way we interact with databases. So if you think about with MySQL, you push data into MySQL. MySQL doesn't pull from your application. So that's the difference. Pull method is great when you have a lot of data and you don't need pre-aggregation. So if you need to store all the requests you have and you don't need to count them, you need to push them and not pull them usually, because the pull can grow and memory is used and can be a problem. So it's not a fight. It's more like you have these two options. You need to support both. You need to have both, and you need to pick the right one for your use case. So for some services, we use a push method. For others, we use pull. So it's not a fight. So we use Kubernetes for our new version of the cloud system, and we work in this way. We have a set of nodes, and in one node we have our stack. So we have InfluxDB and Chronograph. InfluxDB is the database, and Chronograph is the UI. So other than that, we deploy a sidecar to close to every application. If you know a little bit about Kubernetes, Kubernetes has this concept of pod, and pod contains more than one containers. The containers that are inside the same pod, they share the network namespace. So it means that you are sure that they are in the same node and they are close to each other, and you can solve them via localhost. So we deploy Telegraph, that is our sidecar, to the application that we need to monitor. And we configure it to get data out from the application in localhost. So it's not that expensive, and it's really flexible. Because let's say that you have a MySQL doesn't expose the Prometheus API format, so you can't wait for Kubernetes or for Telegraph to get them, because there is no entry point. So you need to have a Telegraph for that. So if you have some specific use case that Prometheus is not able to handle, or Telegraph is not able to get automatically from Kubernetes, you can deploy Telegraph as a sidecar. Other than that, we have a Telegraph in every node, and the Telegraph that is running in every node has a daemon set, is getting system stats from the node itself. So memory, CPU, and this kind of stuff are retrieved from the Telegraph that runs in every node. Okay, that's good. But this is a continuously improving process. So I call it the process of understanding. So you instrument something, you observe how it goes, so you get all the metrics, and you use graph and dashboard to understand the seasonality on how it goes. But at some point, you need to aggregate them together. Because if you have alerts and you are just alerting on CPU, for example, you will get a lot of spams when there is a spike on CPU, but probably you shouldn't wake up for that. Because if you are in a cloud system, cloud should give you the capability to scale. So if it's a CPU problem, who cares? Amazon is gonna spin up more AC2, or OpenStack is gonna give us more resources. So you shouldn't be paged for that. You should be paged if your customer is not able to log in your application, because this is your fault. So you need to wake up and fix the issue. So that's why developers should deploy their application and should manage that, because you close the loop of pain really faster. So if you have an ops team that doesn't speak with the dev team and all this crap, you will have the support team that handles the 24 hours, and they need to page a ops, and they need to page a developer. So everyone will show up in the night and having fun. So it's really good to at least change a little bit who get paged. So developers should be on call. And because they know the behavior of their application, they know what they did wrong usually, and it takes a lot less for them to deploy a fix than somebody else. Other than that, we write a presentation of the service. So every application has a README on GitHub. So we have our README that explains us the critical metrics that we should look for. The capacity planning, so if it's a CPU-intensive application, if it's a disk, if it needs SSD or this kind of stuff, everything is written inside this README, and there is the SRE team is able to understand and take action based on that. So this is important because the developers kind of know what they want. Obviously, it's the operational side of the force that need to validate if it's true, but it's a good cooperation experience. Keep everyone in the loop. As I said before, silos didn't work well these years, so we should change a little bit how we do stuff. So put the team together with different skills, and they will write code, they will deploy it, and they will take care about it. And it's fun. I mean, I had the chance to almost never write code that I wasn't able to deploy. So I'm still alive, and it's fun. So I think you should try. Another stuff that these days it's really important, every crappy code exposes an API. So even ourselves, all the services that we write usually has an API that you can interact it automatically. So this is great because developers can write their own tools, their own instrumentation tools, as they wish. They can drive automation by themselves because there are API available. So in our case, Capacitor obviously has API, and we have a good amount of people that automatically write Capacitor alert via API. So it's the application itself. Then, other than creating chaos and generating pages, it's also the one that is able to create new alert or disable alert because the application knows the state of itself. So let's say that in my case, customers are able to create cluster. So they ask for a cluster with 7, 10 nodes in a particular region in AWS. So the application that takes this request should be also the one that creates the alert that the support team will get when something goes wrong. Because that application is also the one that knows when the customer shut down the cluster. So what usually happens is that a customer shut down the cluster, but the alerts are still there, and the support team get paid for something that doesn't exist. So that's why for some specific use case, it's a good idea to have the application that dynamically creates alerts, or more in general, if you write API, use the API, because there is no purpose for writing them if you don't use them. Code review, it's important. I'm almost sure that nowadays everyone does code review, but I think that we should also look and ask for how we measure a feature or how we understand that code. So this is really important for future purpose. And code review is the best place where you can help your colleagues to instrument your application. Because as it happens to me every time I write a new feature, I write the feature, I put some logs, I put some metrics, but I'm all on the feature. I'm not on the instrumentation code. Sometimes log doesn't have any sense, so it's great to keep in mind, and this is a cultural shift, that as a code reviewer, you can be very helpful about understanding and instrumenting the feature that you are looking for, or the code that you are reviewing. So keep in mind that it's really great. So we don't care, as I said, we don't care about CPU, we don't care about memory, we don't care about this kind of stuff. We care about what our user is doing, and we care about the fact that he can do that well enough. So we care about the user creation, or if the cluster was created, and we create if the invoice was generated, if we are a newsletter company, we care if the email was sent. If we are an e-commerce, we care about the fact that the purchase went well in our site. So we don't really care about how much CPU it took if it goes over. And obviously we care about data, but data is there. Gravity is all about, it's another story, so I'm not going to tell about data. So this is small, but this is a real trace, and this is a story that I learned after instrumenting my application with trace. I call it the cost of a retry, because retry is really important, and it's a pattern that you use in distributed system, because we know that network fails, and we know that sometimes retry is good enough to fix the problem. We don't need to ship rockets in the sky. We just need to retry. So we put a retry, and we put another retry, and we put a retry that retries. So at some point you end up just having retries. So this is a patch in one of our clusters, and you can see that our request failed, and it wasn't able to get done. It was just gonna retry, and this is a cost. This is a really big cost, because AWS has rate limits, so you saturate your API, and you are not able to create another one. So retry are great, but you need to look at how they perform, because sometimes they goes over control. So. Yeah. Another lesson that I learned, I'm just going to have a look at the time. Another lesson that we learned using tracing is that it is an observability tool. So I don't know if you are in the observability versus monitoring kind of situation, but observability helps you to learn from your system. So in a distributed system, what I understood is that it's not simple to understand what's going on. So look just at a try how messy it can be. So if you think about how complex another feature can turn out, it can be really messy. So you need to learn your system. So an observability is all about understanding it. Monitor is more about taking action when you know that something is not going how it should go. But to know how it shouldn't go, you should observe and learn how it should go. Yeah, that was crazy. So in this particular case, at InfluxDB, our orchestrator, the backend for the YAS product, use something that is called reactive planning. So reactive planning is a pattern really famous in robotics. I wrote an article on my blog about that. So you make a plan and you execute the plan. And before executing every step of the plan, you need to check the state of the system. So this is really good in automation and cloud because let's say that you need to create 3 instances and the process failed in the middle. You're going to retry, but you need to check how many of them you already created, the state of them, before generating a new plan that says, I just need to create 2 EC2, or I just need to create 3 EC2 and remove the one that I created because it doesn't work. So reactive planning does this kind of stuff. You have a set of steps, and you check which steps to do in which way. And the steps are able to return other steps based on how the step went. So let's say that one of the steps failed, the one that created the security group. You can retry, or you can delete it. So based on how the previous goes, you can generate other plan, and they recursively get executed. So this is a great pattern, and this is great for observability and tracing because you can trace every step. So if you look, there are 3 steps at least here. One is register cluster node to ELB. Another one is register instances to ELB. So the name is not great, but the idea is that the first one retrieve all the instances for the cluster, and the second one register the instance to the load balancer. And there is another one that is cluster running, that it's a check that we do to understand when the cluster is ready. And to create these 3 blocks, the last 3 blocks, the step is running cluster, return itself if it's not ready. So it goes over that until it's running, or until it exceeds a timeout and it reports that it's not running, and it will never run, sadly. So if you look in the middle of the cycle, there are 3 AWS requests. One is EC2, it goes to the EC2 service. The second one and the third one goes to ELB version 2. So if you are used to AWS, you know what I'm speaking about. But if you don't know, the EC2 service is the part of the API you use to create instances, so servers and virtual machine. And the ELB version 2 is the one that you use to manage load balancer. So if you need to attach servers to a load balancer, you need to create them, and you need to call the ELB service to register them. So there are 3 requests, but sometimes support team or I was looking at cluster that wasn't able that went well, but the instances wasn't registered to the load balancer. So the best stuff I was able to do was to get this trace. Sometimes it was working, sometimes it wasn't, and I wasn't able to get anything from AWS or from my logs. But at some point, luckily, I got this trace, and I got this trace. So if you look deeply on this, you can figure out that this has 3 spans, and this one has 2 spans. So that's where the problem was. For some reason, I wasn't calling one of the spans that I was supposed to, one of the requests that I was supposed to do. So I was able to have a deep understanding about where the problem was. And it's also a good practice to write really small steps. So in really small steps, you can say that, okay, the problem is always an if, that it shouldn't be a if or something like that. So it was easy to fix because I was able to understand deeply where the problem was. So that was great. And AWS has also a really good way, the Amazon SDK in Go at least, but I think also in Java, it has a lot of hooks that you can use. So I use that hooks to trace the application. So tracing doesn't come for free with AWS. You need to do some code, but it's pretty easy. So a specific trace looks like this one. So this is a trace. No, this is a span of the trace. So let's imagine that I'm going to click on the ACQ there, the Amazon ACQ span over there. This is what I get. So I get how much it took, millisecond. I got that I called the Amazon ACQ service with the post method. I get the request body because I'm storing the request body also. And I'm storing the response from AWS. So I know everything about this request. And obviously, this is super expensive, so that's why tracing can be hard to manage and store. But in my case, for my application where there is not a lot of traffic that goes there, but it's a lot complicated, I'm storing everything I can because I need to have visibility on everything every time. So, as I try to say, collecting data, it's a solved problem. So we know how to do that. We have Prometheus, we have agents, we know how to do that. The problem is aggregation, alerting, downsampling, because that's where we need to put all the effort. And to be honest, that's where our brain can help. Gathering data can be done automatically, but looking at the data, getting the right, making the right questions to understand a particular behavior is the challenge. And in the distributed system, this is complicated. So, thank you. I'm very happy that if you enjoyed it. If you didn't enjoy it, let me know. And any questions? No? I'm going to stay here all afternoon, so if you're not going to read out to me that simply, let me know.